So now, if we look at the force, so this is our specific thrust. There's all these names, and quite frankly, I don't remember them that well. So this is equal to m dot times v sub e. So this is looking at the change of momentum, that dmv/dt term, where there have been some steps done. 1 plus RFA minus v sub t over v sub e. And this is equation 1418. So what I did not do is the algebra of dealing with these terms to give me this. And the work, the power, is equal to force through distance. So I have the force acting through the velocity, and so we have this is m dot a v sub e v sub t times 1 plus RFA minus v sub p over v sub e. This is an E. So the maximum work, so this gives us the power, so max work. With so we're going to take the derivative of this term with respect to this, set it equal, and that's equal to 0. And this is 1 plus RFA minus 2 v sub p over v sub e. And so I get that v sub p is equal to v sub e times 1 plus RFA over 2. So for the maximum work, the plane velocity would be about half the exit velocity. They have terms called propulsive efficiency, so there are a couple of other terms we'll mention and look at, and then we'll do an example of a problem with this. Eta sub t is equal to 2 over 1 plus VE over VP. So now we have all this stuff, and so what? And so what we can do is try to make some sense of it. So when VP equals 0, there is specific thrust is a maximum, and this occurs at takeoff. And that's where you need the thrust. So it's like, all right, the velocity is 0, and then goes the engine, and so that gives us the maximum thrust because they need to get going. So this is one thing. Second thing, when VP equals VE, eta sub p is equal to 100%, but the specific thrust is 0. That's not cool. And then V sub E, therefore V sub E should be greater than V sub P. But not much. And so now, this particular aspect about the thrust makes a lot of sense. This one we can understand with the equations, but this one makes sense because we've experienced when we've flown, so we have a sense of that. Now what I'd like to do is look at example 14.8, and we'll go through that, and we'll use different K's and C sub P's for the products as well as the air. And so 14.8. And so with this, we're going to have a diffuser, the compressor, combustion chamber, turbine, nozzle. And let's see, we have 1, 2, 3, 4, 5, 6. So we have our various states. And here at state 1, we have 83 kPa, 230 degrees K. I forgot at what altitude these pressures and temperatures are, but we have that. We have that the velocity of the plane V is equal to 305 meters per second. So this is V sub P, gives us the velocity of the plane. We're going to have the pressure here. This is 480 kPa. T4 is 1400 degrees K. We're going to assume in this case that we're going to let RFA essentially be 0. And all it does is get rid of the RFA in the calculation, so it gets some easier simplifications. We can put it in, makes things a little more complicated just in terms of calculation. And the products, we're going to have K is 1.35 and C sub PP is equal to 1.1. And for air, we know what that is. So let's do the first law on the diffuser. And so I have H1 plus KE1 is equal to H2 plus KE2. But we're assuming it's an ideal diffuser, so the velocity leaving is 0. And so then I separate this, I have C sub P, T2 minus T1 is equal to V1 squared over 2000. So I have, if I bring this, so this is C sub P T2, C sub P T1, put it in, solve. I know V1 is 305, I solve for T2. And so then I have 1.0047 T2 minus 230 is equal to 305 squared over 2000. And so I get that T2 is equal to 276.9 degrees K. And then I can use the reversible adiabatic relationships, PV to the K, to find P. So I have that P2 is equal to P1 times T2 over T1 to the K over K minus 1. So this is equal to 83 over 276.3 over 230 to the 1.4 over 0.4. And so with that, I find that P2 is 157.7 kPa. So I have, it went from 83, it doubled. So it basically doubled going through here, and now I have that to go up. So now I'm going to compress that isentropically through the compressor from state 2 to state 3. To the 3, PV to the K is a constant. And so I have that T3 is equal to T2 times P3 over P2 to the K minus 1 over K. And the T3 is equal to 276.3 times 480 over 157.7 to 0.286, where I get that T3 is 380 degrees K. And I get that WC is equal to minus H3 minus H2 is equal to C sub P T3 minus T2 WC is equal to minus 104.3. So put in T3, T2, and C sub P for air, you get that, kilojoules per kilogram.